All right, welcome to 4.3, curve sketching, this time for rational functions. So, let's review. What do we need to sketch a curve? Well, we can use the first derivative of a function, also known as f prime of x or y prime. There's some other ways to denote it too. You could say dy dx, all sorts of fun stuff. From the first derivative, we can get local minimum and maximum points. And between those points, we can see intervals of increasing and decreasing on the function f of x. The second derivative of f of x, which is also f prime of x, or you can call it y double prime, or there's a way to show it with dy dx too, but I can never keep it straight, so let's not even talk about it. From the second derivative, we can learn about intervals of concave up and concave down for the function f of x. And then between those, we have possible inflection points. All of that stuff we covered in 4.2 ad nauseum. And there's a little bit of it also in 4.3, but we put it all together with asymptotes. So with rational functions, you can have vertical asymptotes because now you have denominators. And so your function can be undefined wherever your denominator is equal to 0. We can have horizontal asymptotes when we take the limit of the function as x approaches infinity or negative infinity, whatever that limit is. If it exists, then that's a horizontal asymptote. And finally, oblique asymptotes, which if you haven't seen them before, they only exist where the degree of the numerator is 1 more than the degree of the denominator. So it's a really special case, and we'll look at how to find that today. All right, so here's an example from the homework. We've got this simple rational function, 6 over negative 3x plus 2. And we're going to go through all the steps using all the tools we know, and then we'll include also the asymptotes. All right, so here's our function. And step 1 wants us to find the intervals on which this function is increasing and decreasing. So remember, we do that by finding the first derivative. All right, so one of the fun things about this section is that all the functions are rational. In other words, they're fractions. So we're going to have denominators. We're going to have to use the quotient rule. We can get around using the quotient rule if we write this creatively, right? So we could rewrite this guy as 6 times the quantity negative 3x plus 2 to the negative 1. And then finding the derivative of it is much easier, right? We can just use the power rule. So negative 1 times 6 gives us negative 6 times the inside, or in terms of the inside, negative 3x plus 2, and subtract 1 from that, and it's negative 2. And then you need to multiply that times the inside by the chain rule, the derivative of the inside, which is negative 3. Okay, so simplifying, negative 3 times negative 6 is 18 times the quantity negative 3x 2 to the negative 2. All right, so that's our first derivative. And then remember, to find the intervals where the function is increasing or decreasing, we need to set this guy equal to 0, because those are our possible mins and maxes. And remember, a min is where the function stops decreasing and starts increasing, and a max is where the function stops increasing and starts decreasing. So let's set it equal to 0. So f prime of x equals 0 is 18 times negative 3x plus 2 to the negative 2 power equals 0. Now remember, another way to write this would be, if we go back to the rational form, we get negative 3x plus 2 squared in the denominator. And so we're looking for that to be equal to 0. Well, there's no way that that's ever going to be equal to 0, right? Because our numerator will never be equal to 0. So nowhere. But remember, another place where you find critical values, in other words, the fences, if you will, the values that separate increasing and decreasing intervals, is where the first derivative is undefined. And that could happen, right? It's going to be undefined where the denominator is equal to 0. So f prime of x is undefined where negative 3x plus 2 squared is equal to 0, or where negative 3x plus 2 equals 0, right? Because the only way you're going to get that whole thing to equal 0 is if what's inside equals 0, and then you square it, and it's 0. So let's see, negative 3x equals negative 2, or x is equal to 2/3. Okay, so when x equals 2/3, you have a critical value. In other words, that is one of the fences that we can split this number line up with. So at x equals 2/3, our first derivative is undefined. Okay, but we want to know what's happening before it's undefined and after it's undefined. So we can test some values. Let's say less than 2/3 we can try 0, and more than 2/3 we could try 1. So f prime of 0 is, let's see, 2 in the denominator, right? Yeah, so squared, so it's 4, so it's positive. So we know that these values are positive. In other words, the function's increasing on that interval from negative infinity to 2/3. And then from 2/3 to infinity, we can plug in 1 here. We're going to get negative 3. Oh, you know, it doesn't matter. It doesn't matter. No matter what you plug in, you have a positive value in the denominator and a positive value in the numerator, because anything squared is going to be positive. So this is also increasing everywhere. Okay. So the function's increasing everywhere, except that it's undefined at 2/3. And in fact, if you look at the original function, at 2/3, we're also going to have 0 in the denominator. So the function itself is undefined at 2/3. So we can't say the function's increasing from negative infinity to positive infinity. We have to say it's increasing from negative infinity to 2/3, which is where it's undefined, and then again from 2/3 to infinity. All right, so they want the answers in interval notation. So negative infinity to 2/3. And then the second interval where it's increasing is 2/3 to positive infinity. Fingers crossed. Oh, I should say it's never decreasing, my bad. I don't know if oh, try again. Okay. It's hard to do this with the, I don't know if it's going to let me click on it. Okay, there you go. There we go. All right. Oh, at least it wasn't the red screen. All right, so the next thing it wants us to do is to find the intervals on the graph where it's concave up and concave down. So we know what to do. We find the second derivative. Same thing we just did, only with the second derivative. Okay, step 2 asks us to find the intervals where the graph is concave up or concave down. So we're going to use the second derivative. So the first derivative is here, so we can use that to find our second derivative. All right, so if our first derivative is 18 times that guy to the second power, to the negative second power, we'll just multiply. Again, we'll use the chain rule. We start out by multiplying negative 2 times 18, so negative 36 times that inside quantity, or u if you like, to the negative 2 minus 1, so negative 3 power, and then multiply that times the derivative of the inside, which is negative 3 again. So we get, gosh, what's 3 times 36? 108. So positive 108 times negative 3x plus 2 to the negative 3 power. Another version of that, of course, would be 108 in the numerator, and in the denominator, negative 3x plus 2 quantity cubed. All right, and just like before, we can set this equal to 0 to get our hypercritical points. It's never going to be equal to 0, again, because we don't have a numerator that can be 0. But it can be undefined where our denominator is undefined. And you'll notice that's the exact same spot, right? Because the only way for this denominator to equal 0, I said that wrong. It's where the denominator is equal to 0 is where the second derivative is undefined. Okay. And the only place where that is going to happen is the same value, x equals 2/3. It's still going to give us 0 in the parentheses, and 0 cubed is 0. So x equals 2/3 is our hypercritical value. And then we're going to use that as a little fence on our number line again, where f double prime of x is undefined at 2/3, which makes sense again because 2/3 is not in the domain of our function. It's not defined on our function. But we want to know where the function's concave up or down. Luckily, we can use those exact same values, 0 and 1, and we'll plug them in this time to f double prime to see where the concavity, what the concavity is. So at 0, we've got a positive in the numerator. Oh, and now we can have a negative in the denominator, can't we, because it's cubed. So 0 down here is going to give us 0 plus 2, which is positive, so a positive over positive is positive. And we have concave up between negative infinity and 2/3. I think we're going to have, let's see, when we plug in 1 to the second derivative, we have a positive in the numerator, of course. 1 times negative 3 is negative 3, plus 2 is still negative 1. Cubed is still negative, because you cube a negative and you get a negative. So we have a positive over a negative, which is a negative, which means that from 2/3 to infinity, our function is concave down. Awesome, let's put that in the homework. Yay! Can't wait to get the grade. All right, so again, interval notation, negative infinity to 2/3, and concave down from 2/3 to infinity. All right, what's the next piece? All right, now they want us to see the maxima, minima, and inflection points. So let's go back and look at our page. All right, so let's first consider maximum and minimum points. Remember, this function is increasing everywhere, so there's never a place where it goes from increasing to decreasing or decreasing to increasing, so there's no maximum or minimum points. And then when you want to look for inflection points, you go to your second derivative. And again, same kind of concept. The inflection points are where your function goes from concave up to concave down, or vice versa. Now we do have a change in concavity here at 2/3, but remember, that's not a point, right? This is 2/3 is a value for x for which the function is undefined. So you wouldn't be able to find a y value even if you thought that that was an inflection point. So it's not a point, so it can't be an inflection point, is my point. Lots of points. So this is actually really fun. You just get to hit no local max, no local min, and no inflection point. Ba-bam! All right. Oh, last step. Now it's going to ask us for the asymptotes. So this is the new part. All right, vertical asymptotes, horizontal asymptotes, and oblique asymptotes. Let's check it out. Okay, so remember, vertical asymptotes are where the function is undefined, and we know now that our function is undefined where x is equal to 2/3. Yeah, because 2/3 times 3 will be 2, or times negative 2 will be negative 2, and that added to 2 will give us a 0 in the denominator. So x equals positive 2/3 is our vertical asymptote. Remember, that's a vertical line, so that's another indicator that you are thinking you're on the right track. All right, what about horizontal asymptotes? Remember, horizontal asymptotes are those ones where your function, as x goes to infinity or negative infinity, as it goes along, it gets closer and closer to some horizontal line. In other words, it like maxes out or minimizes out, mins out. And so how do we find that line where as x goes to infinity, your function approaches that value but never touches it? That's right, don't forget about our limits. So the limit as x approaches infinity, also negative infinity, of our function. Okay. So what is the limit as x approaches infinity of this function? Well, one of the ways you can see it is, you can think of it as 6 is going to stay still, right? But as x gets bigger and bigger and bigger, this denominator is going to get smaller and smaller and smaller, but out to like really giant small numbers, right? So it's going to be 6 over negative 10 million and 6 over negative 27 billion, right? It gets closer and closer to 0. So that's one way of just sort of using your brain to think of it. But another way is that fun tool that we've been using where we divide everything by the highest degree of x. Well, the highest degree of x here is just x, so we would have 6 over x, and negative 3x over x is just negative 3 plus 2 over x. And then the limit as x approaches infinity of all those things that have x in the denominator all go to zeros. So that is equal to 0 over negative 3 plus 0, which is just equal to 0. Okay, 0 over negative 3 is 0. So it does exist. There is a horizontal asymptote, and it is y equals 0. Okay? Now, the oblique asymptotes only occur where the degree of the numerator is 1 higher than the degree of the denominator. Shoot, I still can't say that. The degree of the top is 1 bigger than the degree of the bottom. So that you can do some division, and I'll show you that in the next example. All right, so they're friendly enough to show us x equals, and y equals here so that we don't have to fill that out. Remember, our vertical asymptote was where x equals 2/3. Our horizontal asymptote was y equals 0, and we don't have an oblique asymptote because our rational function is not in the form where you have 1 higher degree in the numerator than in the denominator. All right, good one. Just one last thing before we do another example. This is the graph of our function 6 over negative 3x plus 2. And you can see that we do have a vertical asymptote at x equals 2/3 right there, so pretty, and then a horizontal asymptote at y equals 0. You can also see that the function's always increasing everywhere, which is interesting. It's hard to sort of visualize that where there's a point where it's undefined, right? So it's increasing, and then it's not defined there, but it starts down here at negative infinity, and then it continues to increasing. Now it never reaches that horizontal asymptote of y equals 0, right? But it is continually increasing, which is this really cool paradox if you think about it. It just keeps getting closer and closer to that green dotted line, never touches it. It's magic. All right, so for this example, we're just going to find all the asymptotes. We're not going to worry about increasing and decreasing and stuff. All right, so vertical asymptotes, remember, is where the function's undefined, and it's especially important for rational functions because it happens all the time, right? It's wherever the denominator is equal to 0. So to find our verticals, we just set the denominator equal to 0. 2x minus 7 equals 0, so 2x equals 7, or x is equal to 7/2, and that is the equation of the vertical asymptote. For horizontal asymptotes, we're going to find the limit, because that is in fact what's happening. We're going to find the limit of this function as x approaches infinity. You can also find it where x approaches negative infinity. It's just as important, but I think we're just going to find one here. So the limit as x approaches infinity of the whole thing, negative 4x squared plus 4x plus 15 all over 2x minus 7. And we can use that trick again where we divide every term by the highest degree of the x terms. So x squared is what we're going to use. So this limit is equal to the limit of a similar rational expression. In other words, if we divide each of these by x squared, so negative 4x squared divided by x squared is negative 4. 4x divided by x squared is 4 over x. 15 over x squared. 2x over x squared is 2 over x. and 7 over x squared. Now, we know that as x approaches infinity, each of these terms that has an x or an x squared in the denominator will all go to 0. So we have the limit then, as we evaluate the limit, is negative 4 plus 0 over 0 minus 0, that's 7, which gives us a 0 in the denominator. So it does not exist. Okay, so there is no horizontal asymptote. We should check also where x approaches negative infinity, but it's the same thing. Where x approaches negative infinity, all these guys are going to go to 0. It doesn't change. Yeah. So no horizontal asymptotes. And then finally the oblique asymptotes, which is new to us in this class. Oblique just means diagonal. All right. So the oblique asymptotes are when you have a numerator whose degree is 1 higher than the degree of the denominator. And we have that here, which is why I chose this example. And the way you find it is you divide this numerator by the denominator. When you have a monomial in the denominator, it's super easy. You can just write it as the sum of 3 terms, in this case, if this were a monomial. But because we have a trinomial divided by a binomial, we have to use division, which I'm sure was your favorite part of math 116. All right. So 2x minus 7 goes into negative 4x squared plus 4x plus 15. And I'm just going to use regular division. If you love synthetic division, it's kind of fun too, but this way, I think, illustrates what we're doing a little bit better. All right, so 2x goes into negative 4x squared, negative 2 times, negative 2x times. All right, negative 2x times this binomial will get a negative 4x squared. Negative 2x times negative 7 is plus 14x. Subtracting, I get a 4 minus 14, or negative 10x. And then I bring down the 15. 2x goes into negative 10x. Negative 5 times. Negative 5 times this binomial is negative 10x plus 35. Subtracting again, I get 15 minus 35, or negative 20. So our function, which was this big old rational function, negative 4x squared plus 4x plus 15 all over 2x minus 7 can also be written, if we do that division, it's just another way of writing this function, as negative 2x minus 5 minus 20 over 2x minus 7. It's just an equivalent way of writing this guy. But what's lovely is your oblique asymptote is this piece right here. So not this piece. You want to make sure that this last bit right here goes to 0 as x goes to infinity. So the limit of this last piece as x goes to infinity should be 0. And if that's the case, then your oblique asymptote is y equals negative 2x minus 5. Done. There it is. All right, here's my favorite part. Here's the graph of that function that we just found the asymptotes for. Looking at the vertical asymptote, you can see here's x equals 7/2. It's lovely, and if you scroll, or if you zoom out, you can see how those two pieces just hug that asymptote. And then you can see that there's no vertical asymptote, because as you go off to infinity, these functions are not leveling out horizontally. But there is an oblique asymptote. Isn't that cute? Oops, back up. And now you can see that the same thing's happening with that diagonal oblique asymptote. So cool. All right, have fun with your homework, friends.